Hey everyone, welcome to another Explainer. Today, we're diving straight into the fascinating, unseen forces shaping the moon. We're breaking down the incredible science behind the lunar atmosphere. Yes, you heard that right, atmosphere. And exploring the engines that drive it, as well as the ancient treasures hidden right inside it.
So, let's kick things off with a question that might just turn everything you learned in grade school upside down. Does the moon actually have an atmosphere?
Think about it. We're so used to contrasting Earth's thick, cozy, life-protecting blanket of air with the moon's totally barren, empty vacuum of space. It's an easy mental shortcut, right? But as we're going to see today, that's actually a massive misconception.
Because here's the wild truth. The moon absolutely has an atmosphere. And get this, NASA and the Lunar and Planetary Institute found that roughly 3 to 4 billion years ago, it possessed an atmosphere that was actually twice as thick as modern-day Mars. And even today, while it's much thinner, it has a complex atmospheric system that features an extended tail made of sodium that literally trails behind it in space. How cool is that?
All right, so here's our roadmap for today's Explainer. We'll cover the moon's hidden atmosphere, volcanic and tectonic impacts, the meteorite broom effect, lunar volatile findings, exploring the cold traps, and finally, the Artemis 3 mission.
Section 1. The moon's hidden atmosphere. From ancient skies to a modern exosphere.
You know, the moon's environment has gone through some radical changes over the eons. By studying Apollo magma samples, scientists figured out that about 3 to 4 billion years ago, massive volcanic eruptions pumped out huge amounts of gases. This actually created a thick, temporary atmosphere that stuck around for a staggering 70 million years. But eventually, relentless solar winds stripped that ancient sky away, leaving us with what's there today.
And today we call that incredibly thin envelope of gases an exosphere. This is an atmosphere so tenuous, so incredibly thin, that the gas molecules rarely even bump into each other. Just to put that into perspective, a cubic centimeter there has about 1,000,000 billion. That's 10 to the 15th, times fewer molecules than the air you're breathing right now on Earth. So yeah, practically a vacuum to us. But trust me, it is highly active.
Moving on to Section 2, Volcanic and Tectonic Impacts, the Internal Engines of the Moon.
So deep beneath the lunar crust, there is this incredible internal engine churning away. Radioactive potassium-40 naturally decays over time, and that creates a noble gas called argon-40. But it doesn't just stay buried. That argon-40 actually percolates and seeps all the way up through tectonic faults to the surface. Instruments on the Chandrayaan-2 orbiter actually caught this in action. During the freezing lunar night, the gas condenses, freezing onto the dirt. Then, at dawn, when the sun heats things up, it releases right back into the exosphere. It's almost like a continuous, rhythmic breathing, all driven by the moon's deep tectonic forces.
Section 3. The meteorite broom effect, the external engines of the moon. Now, internal tectonic seepage isn't the only engine running up there. Because the moon doesn't have a thick shield like Earth, it gets continuously pelted by space debris, everything from big meteorites down to tiny, pin-sized micrometeoroids. This sets off a violent reaction called impact vaporization. These rocks are coming in hot, often traveling faster than 21 miles per second. The impact generates so much intense heat that it instantly vaporizes the lunar soil and the meteorites themselves, throwing fresh atoms straight up into the exosphere. NASA's LAD-D mission actually saw massive spikes in atmospheric gases right when the moon flew through dense meteoroid streams. In fact, recent research by an MIT team led by Nicole Nee finally settled a huge, long-standing debate about what actually sustains this atmosphere. They looked at heavy and light isotopes of elements, like potassium and rubidium, from Apollo soil samples. Because lighter isotopes get blasted into space much easier than heavier ones, the leftover ratios in the dirt act like a chemical fingerprint. And they proved, without a doubt, that this violent, never-ending bombardment is actually the dominant creator of the lunar exosphere. NASA has this brilliant analogy for it. Imagine the moon is like a dirty rug. It's just constantly getting whacked by this invisible micrometeorite broom. Every single hit kicks up a fresh haze of dust particles and atoms into the near emptiness of space. Then they settle, or escape, only to get kicked right back up again.
Section 4. Lunar volatile findings, the treasures hidden in the exosphere. All right, so we know all about the engines kicking up this dust, but what exactly are the treasures floating around in it? Well, the exosphere is surprisingly rich with a mix of what scientists call volatiles. First off, there's water vapor,
a lot of which is actually delivered by those smashing meteoroids we just talked about. Then we have that argon-40 bubbling up from radioactive decay. There's also helium, mostly brought in by the solar wind, those highly energetic particles constantly blowing off the sun that would only stick around a few days before floating off. And maybe the craziest one, sodium. It gets knocked off the surface and literally pushed by solar radiation to form a massive glowing tail, stretching far behind the moon's night side.
But here's the thing, these precious volatiles don't just stay floating in the exosphere indefinitely. They eventually get trapped. They might latch onto the surface of microscopic grains, get sealed deep inside volcanic glass beads from those ancient eruptions, or hide away in discrete underground deposits. And it's these exact physical treasures that scientists are so eager to study.
Section 5. Exploring the cold traps, where the water hides. So, as those water vapor molecules are freed by meteor impacts, they kind of just randomly bounce across the lunar landscape. And since the moon has virtually no atmosphere to trap heat, the temperature extremes are absolutely wild. Eventually, a lot of those bouncing water molecules migrate toward the lunar poles, where they stumble into regions of permanent, pitch-black shadow inside deep craters.
These permanently shadowed regions act like the ultimate sinks. The temperatures drop so incredibly low there that the water molecules just slow down and freeze solid. We call these cold traps, and they are a massive deal for planetary scientists. Why? Because they preserve billion-year-old water ice. They are literally a frozen time capsule from the early days of our solar system, locking away untouched records of ancient volcanic eruptions and ancient cometary impacts.
Section 6. The Artemis 3 mission. Humanity's return to the lunar surface.
And that brings us to the incredibly exciting culmination of all this science. For the first time in over 50 years, humans are heading back to the lunar surface. Artemis 3 is going to land astronauts right smack in those volatile-rich south polar regions so they can sample these ancient frozen treasures firsthand.
The science goals here are just huge. To really study these volatiles properly, the astronauts can't just scoop up some dirt in a bag. They're going to use hermetically sealed, double-vacuum cryogenic containers to bring these super delicate ice samples all the way back to Earth. If they didn't keep them deeply frozen, the water and fragile gases like argon would just melt and escape on the ride home. They're also setting up long-lived geophysical networks to constantly monitor those seismic ticks and exosphere changes we were talking about earlier.
But, there is a catch. The very act of landing a massive spacecraft on the moon releases tons of anthropogenic or human-made exhaust and water vapor. Studies are already showing that even a single landing will temporarily but very significantly alter the exosphere and spread gases globally across the whole lunar surface.
Which leaves us with a pretty provocative thought to wrap up on. The moon's exosphere is this beautifully delicate, perfectly balanced system driven by billions of years of meteorite impacts and deep tectonic breaths. So, as we finally reach out to touch this pristine, ancient atmosphere and harvest its frozen water, how much will our very presence inevitably change it? It's a massive question that scientists are racing to answer right now. Thanks so much for joining me on this explainer, and keep looking up.